Then so far we have finished the what's the inside of a router. And then let's continually to move on to the IP Internet protocols. Here we will talk about the datagram format, IPv4 addressing, ICMP, and also the IPv6. As we know, for the network layer, not only the end systems will implement a network layer, but the routers will implement the network layer as well. And there are three types of protocols will be implemented on the network layer. One is IP protocol, this one, which is addressing the conventions, the datagram format and the packet handling conventions. Another one is ICMP protocol, which uses to handle the errors for the datagrams and also the router signaling will do this kind of things. In the later part of this chapter, we will talk about more details about the ICMP protocol. And the third one is a routing protocol, which is used to generate the local forwarding table. However, in our normal end systems, we only implement these two protocols, which are IP protocol and ICMP protocol. Only the routers will implement the routing protocols. Then I see the IP datagram format. And for each line is 32 bits long, and in the header field include a numbers of field, and let's introduce them one by one to see what's the meaning for each field. First, let's see this WER, which represents the IP protocol version number. The second one is a header length, which indicate the size from the beginning to the options. So how large the header length will be, and it will be counted by bytes. For the type of surveys, which indicate the type of data, for most of the case, here just to indicate is it's a UDP data or TCP data. However, for some other situation, the ICMP message will be indicated here. It will show the ICMP type. And then is the time to leave field. For this one to indicate the maximum number remaining hops, which is decremented at each router. Actually, for this field to represent how long or how many hops this datagram can be traveled in the internet. And the reason to have this kind of a field is for to save the internet resources, because we don't want the datagram can transfer or travel in the internet forever. If there are some error happened, so if we don't have a mechanism to stop a datagrams, so for the datagram, the error datagram will be just travel in the internet forever. It's just wasting the internet resources. So and also for this time to live, we have a maximum number is just 255. But for most of the case, we just gave an initial number as 64 to this time to live. And the toward is a destination of this datagram. So each time it arrives on router, this time to live will deduct by 1. And there are two results or two consequences for this datagram. One is this datagram arrive is a destination. Another is the time to live run out of the count and becomes to 0. then the routers will just simply discard it, because when the time to live becomes 0, means this datagram cannot reach its destination. So we don't want to waste the internet resources. So therefore, we just let the router to discard it. And for the next one, the upper layer, which indicates the upper layer protocol to deliver payload to either is a TCP protocol or a UDP protocol, will be goes here. And the length here, which is different from the header length. For this length will indicate the total datagram length, and also counted by bytes. It will be show how large the entire datagram will be. After the length, these three fields will indicate or will use for the fragmentation and the reassembly, which we will talk about in later slides. And these three fields are 16-bit identifier, flags, and also fragment offset. For the options, for example, the timestamp, the record route taken, specify list of routers to visit for this kind of information. If the developer they want to add it into the datagram, they will be goes here. And for the last part, is the real data. It typically just a TCP or UDP segment. However, if the type of service indicate ICMP type, the ICMP message will be goes to this area. And then let's see when we reach when the message on the application layer reach to the network layer, how much overhead will be added into the original data. So let's see the first 20 bytes of a TCP, which is the TCP header, will added into the original message. Another 20 bytes of IP header will added into the segment, and combined together we get the datagram. So when we reach to network layer, in total we will have 40 bytes plus the application layer overhead. So in total, it will be more than 40 bytes of overhead added to the original data. And later, when we deliver this datagram to the link layer, we will add another headers for the link layer to become a frame and transfer to outside of this device. So there are a lot of overhead will be added into the original data. Then let's see the IP fragmentation and the reassembly. So the network link layer have MTU, which is shorted for maximum transmission unit, the largest possible link level frame. So that means there for each frame there is some restriction, and for different link types they may have a different MTU size. But normally for the normal link, the restriction size is 1500 bytes. Therefore, if the larger IP datagram around on a router, the router because the next hop cannot transfer the larger datagrams due to the smaller MTU restriction. Therefore, the larger IP datagrams will be divided into a smaller size uh, datagrams, and for these actions, we call it a fragmentation. Then the one datagram will become several datagrams, just like the illustration here. So for this router, it will send larger datagrams to this router because this link, it can transfer the larger datagrams. However, when the larger datagrams arrive on this router, but the next link can only transfer smaller size of a datagram. Therefore, this larger datagram will be divided into a smaller pieces. In this case, it will divide it into three smaller datagrams. And for this smaller datagrams can only be reassembled at the final destination, becomes a single larger datagrams when it arrives at the destination. And the IP header bits will be used to identify and order the related fragments, as we already see in the datagram of format. Actually, is this field here. Now let's move on.
Then let's see an example of IP fragmentation and reassembly. So suppose the larger datagram with a size of 4,000 bytes. However, the next link can only support the frame size is 1500 bytes. Then the original larger 4,000 byte of a datagram will be divided into a smaller pieces. And in this case, this bigger datagram will be divided into three pieces. And for the first two smaller datagram, each one will be 1500 bytes. And for the third one is 1040 bytes. And then let's see the original datagrams. So since we already know when the segment pass into the network layer will add 20 bytes of IP header into the original segment. And therefore, in this 4,000 byte of datagrams, there are 3980 will be the segment or the original data plus the 20 bytes of IP header. And also for each smaller datagram, still with 20 bytes of IP header. Therefore, for the first two smaller datagrams, each one with 1480 bytes of real data, and for the other 20 bytes is the IP header. And for the last one, the first 1020 bytes will be the real data and or the segment, and the last 20 bytes will be the IP header. And then let's do a calculation for the offset. So how to get the offset? Actually, the offset is just the first byte of each datagram. So for this first smaller datagram, which is from byte 0 to 1479. Therefore, the first byte is 0. Then we can get the offset as a 0. And for the second one, is from 1480 to 2959. Therefore, the second offset will be 1480. However, we can see here it's a 185, which is not a 1480. So how to get this 185 offset? Actually, they use a trick because they don't want to use a larger number for the offset. Therefore, they just use the 1480 divided by 8, and then they can get 185 for this number. And for the third one, this datagram will start with 2960 byte all the way to the end. And for the offset 370, I just use 2960 divided by 8 and then get is 370. And then we will know, we already know how to calculate the offset. And for each datagram, they will, each piece of the original datagrams, they will with the same ID number, which is the X. And for the flag, if the flag equal to 1 means after this smaller piece of datagram still have more data. Just like the first one, we will know there will be the second one. And after the second one, we will have the third one. However, after the third one, because the flag will here is equal to 0 means this is the end of the original datagram. So that's the meaning for the flag. And then we have finished the datagram format for the network layer. And then let's continue to learn the IPv4 addressing.
Then let's see this IP addressing. So here we are talking about the IPv4 version. Therefore, for each IP address, it has a 32-bit identifier, which is used for identify the host or router interface. And for example, here we have an example, which is 32-bit to represent an IP address. And for every 8-bit can be used to represent a number or a decimal number. Therefore, the 32-bit identifier or IP address can be converted to this format, which is 4 numbers, and between 2 numbers, we can use a dot to separate them. And for this format, we call it dot decimal notation. And for each number will be represented by 8-bit. So that means the range for each number is from 0 to 255. And then let's see another important notation, which is the interface. The interface is a connection between the host or router and the physical link. So usually the routers will have multiple interfaces. For example, on the right side, this figure shows us the router in the middle has 3 interface because it can connect 3 internet or 3 networks together. And for the normal host, typically has 1 or 2 interfaces. For example, the wired Ethernet or the wireless interface. For most of the desktop, it will combine with the wired Ethernet and also may combine with the or embedded with the wireless interface. However, for the mobile devices, for example, the cell phone or the tablet, or even right now the laptop, most of the laptops, they only embedded with the wireless interface. And each interface will be associated with an IP address. So that means if the this router has 3 interfaces, so that means it will associated with 3 IP addresses. Then let's see this question. So how are interfaces actually connected? So I'm not sure if you guys still remember in the chapter 1 we have a talk about how to connect the computers or devices together to form a network, and also what kind of devices we can use to connect multiple networks together to get internet. I remember I said the routers can connect multiple networks together and form a larger or form an internet. However, so what kind of devices we can use to connect multiple devices together to get or constitute a network? Actually, the answer is one is we can through switches to connect multiple devices or interface Ethernet interfaces together to form a network. Actually, there's another way we can connect multiple devices together wirelessly. Actually, it's the Wi-Fi base station, or most of the time we call it access point. So through these two kinds of devices, we can connect the multiple interfaces together. Then let's see the subnets. So for each IP address, actually it contains two parts. One we call it the subnet part, and also for this subnet part is a high order bits. Another part is the host part, which is the low order bits. So what's a subnet? Device interfaces with the same subnet part of IP address, which can physically reach each other without intervening routers. So actually it means under this subnet, all the devices, they has the same subnet part, but with different host part. So for example, let's see this subnet part. And also you can see for all the first three decimals, they are exactly the same. And for these four interfaces. However, the last decimal or the host part are different. For this device or this interface is 1, this is 2, 3, and 4. Then let's see the recipe. So how to determine the subnet. So in order to determine the subnets, we just detach each interface from its host or router. If it creating S-lanes or of isolated networks, then each isolated network will be called a subnet. So for example, on the right side, this figure, there are 3 subnets. If we disconnect here, here, and here, we will get 3 subnets. And then let's see another very important concept, which is a subnet mask. So the subnet mask means start for example here the backslash 24 means for each IP address under this subnet, start from left the first bit to the right, we count it for 24 bit, or this 24 bit will represent it as the subnet part, and for the last 8 bit will be the host part. The last 8 bit actually is it can represent a decimal number. Therefore, this 3 decimal number is the subnet part, and the last one is the host part. And from here we can see it. And usually the host part, we will use a 0 to represent it. However, if we have a subnet mask which is 16, and we still use this example, it will be written like this: 223.1.0.0, because for the last two decimal numbers will be represented as the host part. So here we have a question. In this figure, you can count by yourself. So how many subnets within this figure? Actually, the answer is 6. Maybe you get it surprised why I got a different number. So let's count it together. The first subnet is this one. The second one, third one, the fourth one, the fifth one, and the sixth one. Because within each red circle, all the devices or all the interfaces, they will share the same subnet part and with a different host part. If you are not sure about that, you can calculate or check it by yourself. Then let's see the IP addressing CIDR. So in the early age, the subnet mask can only be 8, 16, 24, this kind of numbers. So that means they divided the subnet only by each decimal number. So for example, 255.255.0/24. So with this IP address domain, we will know for the first 24 bit represent the subnet mask, and only the last decimal number is the host part. So under this domain, we can only have 256 IP address can be used by end users or the devices. However, for most of the area, usually at least 2,000 IP address will be needed. If that's the case, so apparently this kind of domain is not big enough. However, in the early age, we only have a 24, 16, or 8 as a subnet mask number. So if we want to get more than 2,000 IP address domain, so we should use this one, which is a 255, 0, 0, and 16. So that means only this above and also include this kind of domain, it has more than 2,000 of IP addresses. However, under this domain, we will have this much of IP addresses. So if we only use the 2,000 IP address, so you can calculate how much IP address will be wasted, because if the IP address are assigned to this area, it cannot used by others. So that means for this more than 63,000 of IP address will be wasted. Then the engineers, they have this kind of idea. We call it classless inter-domain routing, which is a subnet portion of an address of arbitrary length. So the address format will be a.b.c.d/x, where the x is the number of bits in subnet portion of an address or addresses. Therefore, since we can divide the subnet part and the host part wherever we want, then we can have an example like this. So for this domain, the first 23-bit will be the subnet part, and for the last 9-bit will be the host part. And under this domain, we can have a 512 IP address. And if we want to have a 2,000 of IP addresses, so we just add 2 more bits into the host part. Actually, we can have more than 2,000 of IP address, and we don't need to waste this much of IP addresses, which cannot used by other area or other users. Then let's see. So we talk about the IP address. Then the question is how to get an IP address. So where we can get an IP address? The first solution is we can ask the network administrator to get an IP address. Then we can write it down in notes, and when we get back, we open our computer, and through this path, if you use a Windows computer, and then you can manually to tap the IP address given by the network administrator to this location. If you use the Unix system, you can open this file and put your hard-coded IP address there. However, we know that for this way we do it is a constant way. So we have another way to do it, which is through the DHCP. The DHCP is shorted for the Dynamic Host Configuration Protocol, which can dynamically get an IP address from server. And also we call it plug and play because as long as your network support a DHCP server, and everything will be done automatically. So there's no interaction with the network administrator or the end users. So as long as you plug your computer into the internet, so you will get an IP address from the DHCP server. Then let's see the goal of DHCP is allow the host to dynamically obtain its IP address from the network server when it joins the network. Therefore, the DHCP can provide the user with more useful information, which is more than IP address, which we will talk about in later slides. And for internet service provider, if under this internet service provider, they will provide network service to more than 2,000 of customers under this network. But usually there's no more than 400 users use the internet at the same time. Therefore, the internet service provider only need to maintain probably 512 IP block will be enough for the users, because the IP address can be returned by the users and also can be reused by other users. So through this way, compare with the constant way, we only need to maintain a 512 IP address is enough. However, if you use a constant way, you will assign more than 2,000 IP address to these users, and for each IP address is constantly used by that user and cannot used by others. So that's the advantages of DHCP. And then let's see the DHCP overview, or how the DHCP works. So the DHCP server, now start from the host actually. The host will broadcast a DHCP discover message, and then the DHCP server will respond with a DHCP offer message back to the host, and then the host requests the IP address with the DHCP request message. And after the DHCP server receives this DHCP request message, and then the DHCP server will send an address with the DHCP ACK message back to the host or the normal user. So suppose here we have an example. Suppose there's a newly arriving DHCP client. It needs an IP address in this network. And also we know under this network there is a DHCP server. Then let's see how they interact with each other and how the arriving client get an IP address from the DHCP server. So first, the arriving client initialize the communication to the DHCP server, which is DHCP discover. And also, this message will be broadcast through the broadcast way, which is there a DHCP server out there? And with this kind of information. And when the DHCP server receives this DHCP discovery information or message, it will send a DHCP offer, which is also through the broadcast way, and send I am DHCP server. Here is an IP address you can use. Then send it back to the arriving client. When the arriving client receives this DHCP offer, it will send a DHCP request and send it back to the DHCP server. And also through the broadcast way, it will say, okay, I will take that IP address. And here is the details of this DHCP request. Then the DHCP server will give a response for this DHCP request as a DHCP ACK. Still use the broadcast way. And the details is okay, you are got that IP address. And here is the details. Here actually I have a question to you guys. So why the communication between this the DHCP server and the arriving client, why they use the broadcast way to do the communication? So for the first message send it from the arriving client to the DHCP server, we know it's a DHCP discover, because the arriving client doesn't have the IP address of this DHCP server. Therefore, that's the reason why the arriving client will send a broadcast information to the entire network. And then when the DHCP server receives this DHCP discover, it also uses the broadcast way to send the DHCP offer back to the arriving client. And also because the DHCP server doesn't know the IP address of this arriving client, because the arriving client doesn't have an IP address yet, right? And then when the arriving client receive this DHCP offer, actually it already knows the IP address of this DHCP server. But why the arriving client still send a DHCP request through a broadcast way? Why are they doing that? Because in the internet or in this network, there may be more than one DHCP servers. So the arriving client can only take one offer among them. Therefore, the arriving client needed to notice other DHCP servers. Okay, I will take the IP address from this DHCP server. That's the reason why the arriving client will send a broadcast DHCP request back to this specific DHCP server. Actually, it noticed all the DHCP servers under this domain. And then when the DHCP server received this DHCP request message, it still used the broadcast way to send the DHCP ACK back to the arriving client, because before the DHCP server confirmed this IP address or given this IP address to this arriving client, the arriving client still doesn't have an IP address. So that's the reason for the entire communication between the DHCP server and the arriving client. They will use the broadcast way to do the communication. And also, the DHCP server not only can provide an IP address to the end user or the newly arrived devices or client. The DHCP server can also provide extra information, as we already mentioned in the previous slides. It can also provide the address of a first hop router for the client. Actually, it's a gateway router. Another information is the name and the IP address of the DNS server. Usually, the name and IP address is for the local DNS server. And also the network mask, or we call it subnet mask, which is a very useful information for the newly joined in users.